Thank you for attending this presentation. I was not sure I would have a lot of people in the room because it's a very special topic, but I see that there is interest, so I'm very gratified. My name is Vincent Lextrait. I am the founder of a company in the Bay Area. The company's name, Metaspecs. We specialized in specification level tools to produce enterprise applications. A little bit of housekeeping. I'll take questions at the end. Please take note of the slide number if there is a specific slide that triggers questions so that we can get back to them. So the talk is about C++ for enterprise applications. It's a vast topic. I'll try to go as fast as possible, sometimes at the expense of being a little simplistic. I apologize in advance when I simplify too much. So without further ado, let's move to the agenda. First, I will cover the fact that I believe that within enterprise applications, C++ is in front of a paradoxical situation. I'll try to give my take, my explanation on why this paradox exists. And if you disagree, by the way, please feel free to comment. And then I will try to show that C++ can do way better. I'm very tempted to say way better than existing frameworks. And when I say existing frameworks, I mean existing frameworks in other programming languages, notably Java, PHP, or others. And I will take then three examples which are central to enterprise applications. I could have taken many more, but these three ones are I think, very key examples. I will take first referential integrity, which is a property of relational databases. Then I will take as well automatic destruction of objects. And I will show an algorithm that is neither garbage collection nor reference counting, and which is sitting very nicely in between of these two techniques. And last, I will finish with replacing SQL with C++ functions, and replacing it in a way which makes the replacement much faster. So let's get started. I say that C++ is facing a paradox, and this paradox is not an obvious one because on one hand, if you count the market share of C++ in the number of backend transactions processed in the world as I speak, C++ is one of the largest shares. Second, large enterprise applications are mostly C++ based. I've been contributing during more than 20 years to the largest one, which is Amadeus, which is processing 40,000 transactions a second on average, and it is mostly C++ based. Yet, if we look at C++ share in number of enterprise applications, that share is very small. Small to the point that it is considered unpopular. Why? My explanation of that is that our community tools are inadequate or absent. And because of that, only medium to large companies, companies with deep pockets, can afford compensating and building their own. Typically, they build their own application servers. So this leads, and it's a side comment, to the general misunderstanding that C++ is not meant for large-scale abstractions. Elevating the level of abstractions, as Bjarne was saying during his keynote, is not for C++. And C++ is only meant for low-level software, infrastructure software, and should stay there. Yet, you may be aware of this or not, in a number of large technology companies, C++ is elevated to specification, meaning that you describe the how, you don't describe the what, and the specification is compiled, and the C++ compiler is actually automating the production of code. So when Bjarne was talking about elevating C++ abstractions, it is actually being done. It's done in very large companies, essentially. I guess that also small companies do it, but it's not very very famous, and there are not many companies talking about that. One slide about enterprise applications. It's here that I need to apologize. I'm being very, very simplistic on this slide. The need is to handle persistent data concurrently. Enterprise applications are so much more than this, but if we need to explain what it is in 4 words, this is my take. We have lots of data that do not fit in memory. We need to rely on databases because we need persistence, but we need also not to overcrowd the memory. We need fast response time. When I say fast response time, some people are even talking nowadays of instant response time. So instant is impossible in our industry, but what does instant mean? It means technically a round trip which takes less than 350 milliseconds, give or take. And this is perceived as instant by a user. So we need fast response time, and when you reach instant response time, users are not complaining any longer. We need scalability, we need availability, we need fault tolerance. Actually, the right technical term is partition tolerance. And we need consistency. I'm listing consistency as the last of the interesting property because there is a growing understanding that consistency is maybe not the most interesting property because it has very little effect on the business itself, while all the others have a very, very significant impact on the business. So enterprise applications, as I listed them, are a perfect example, maybe the perfect example of what Bjarne is calling a constrained environment. Being in a constrained environment doesn't mean to be small. You don't need to be an embedded system or a device driver which is under stress to be in a constrained environment. It can be a very large-scale environment with thousands of servers. Yet, all the constraints that I listed make enterprise applications a very constrained environment. So it should be a perfect playground for C++. And I hope that my presentation will show that it is. In enterprise applications, everything starts with data types and relationships. In the old times, we were calling this data models. I will explain that I don't use this term any longer. This is contrary to what you are taught. Many C++ practitioners, prominent C++ practitioners, tell you everything starts with algorithms. In enterprise applications, there are very few algorithms. There are some, but not a lot. The reason for that is the 350 milliseconds. Of this 350 milliseconds response time, a lot is eaten up by the network, a lot is eaten up by the database. There's not much left for the application. So traditionally, this may change one day, traditionally enterprise applications have very few algorithms. At the same time, they have a lot of types, and potentially much more than what enterprise applications use currently, and a lot of relationships between these types. Because there are a lot of types, because there are a lot of relationships, data integrity issues happen. And it's not something new. You have data integrity issues with the STL, with algorithms and iterators. You can be in situations where iterators are invalidated. They are not actively invalidated. You should not use them. So this is a small example of data integrity issue. Enterprise applications are full of them. What we can say also about enterprise applications is that productivity is very low. Whether you hire extremely talented people, very smart people, who work at large-scale enterprise applications, they will still tell you that their job is very repetitive. And it's very sad. It's very sad because software is meant to automate repetitive tasks. Yet, nowadays, there is still no real big model to prevent these repetitive tasks to happen. There is very little real use. When you use a relational database schema, you're not expressing something which is extremely reusable. It's not object-oriented, by the way. There are high testing costs. And something which is also very quite specific to enterprise applications, agility collapses after some level of complexity. And that level of complexity is not a very remote horizon. I would hate to give a very silly figure at you, but let me give a figure nevertheless. When you have an enterprise application with a traditional approach and you reach, let's say, 50 tables, you start feeling some pain. It's not utter pain, but there is some pain happening. So that collapsing of the agility does not happen with other domains of application for C++ or other programming languages. It is really very specific to enterprise applications. And it is very simple to understand. It's due to the fact that many databases require indexes to exist. And if you are pushing your data model, it's the last time I used the word, if you push your data model towards being very, very fine-grained, very detailed, when you execute processes, you cross a lot of indexes. And this is extremely costly. At the same time, as we all know, SQL is not object-oriented. So in a use case, when you express an SQL statement, if you have a very, very fine-grained data model, you end up with SQL statements that are not very stable. So the more types you have in your enterprise application, the more pain you endure. What is the wall? I cannot tell you. The wall is 200 types, 300 types. It depends on the application, of course. But it's very, very close. So all these problems that enterprise applications suffer are telltale signs of insufficient abstraction. And so it means that we should raise the level of abstraction. And we should study very carefully from where we start. Because of all these problems, people have tried repeatedly to generate code from specification. That's one way of taking the problem. So you try to gather specification talking with business analysts, and then you collect something which is structured, and you generate code from this. This has always failed, unfortunately. So why are our C++ tools inadequate? Let's talk about relationship. I said that enterprise applications are full of relationships. What do we have to describe a relationship between two objects on the heap? We have unique pointers, we have shared pointers, and that's all. So this is very, very insufficient. And it does not carry a lot of behavior. It describes lifespan, that's about all. When I was talking about referential integrity, for instance, there is nothing of the kind in unique pointer and shared pointer. Boost is very useful. We use it extensively. We love it, but it falls short. What do we have in Boost? We have for enterprise applications. So this projection of Boost for the needs of enterprise applications. We have ASIO. ASIO is extremely useful, but it's network level. So it's not a very high level of abstraction. We have UUID, we have log, we have chrono. We have a few things, but this is very, very short, especially compared to the tools that other people have with other programming languages. Look, we don't even have an application server. People have to develop their own. It's very sad. It's not extremely difficult, but when you are a company and you invest in your own application server, you're diverting resources that should be better directed towards serving better functionalities, having instant response time, rather than building infrastructure software. As you know, C++ offers zero-cost abstractions. So this paves the way towards layered abstractions. So elevating abstraction is possible with C++ by stacking abstractions on top of the other. Some people call it hyperautomation. I sometimes call it hyperautomation. I think I hate the word because automation is not abstraction. Automation is trying to imitate exactly what a person would do. If you look at structured programming, for instance, structured programming is not automation of what assembler programmers do. It's not going to do exactly the same thing. Structured programming is opinionated. It is a methodology. I prefer the word hyper-abstraction, and that's what we do. That's what we suggest the industry does. So let's use layered abstractions. But maybe first, let's learn from the past. People started, as I said, from specification, trying to generate code from specification. 40 years ago, and there are some people in the room, I see gray temples, who were in the industry in the 1980s. I certainly was. And the 1980s was in love with flowcharts. Flowcharts were diagrams aiming at describing code. The fashion lasted 2-3 years, and then it was over. Everybody remembered this until 20 years after, when UML came. UML was not the first one. There were a few others before. UML is the notable one. It's a notable one because people tried very, very hard with UML. People will never try as hard as UML has tried to produce applications from diagrams. UML was 20 years ago. Now we have no code. And again, people are fascinated by diagrams and thinking that diagrams are the solution to bridge the gap between specification and hardware. I have to remind everybody that nobody will try as hard as Grady Bush. And Grady Bush considers, I don't want to speak for him, I apologize if I'm misrepresenting his opinion, but I think that Grady Bush would consider UML as a relative failure. And it taught us a few things. UML is very rich, but the very reason why UML failed is because UML is not precise enough. In spite of the hundreds of diagrams that it provided, UML was still too high level. It was not the only source of information to produce an application. So we need a different approach. Maybe we always tried to bridge specification to hardware from the wrong side of the riverbank. It's true that it's always been tried from specification. It's never been tried from hardware or from low-level abstractions. So the solution might be to start the bridge from the other side. That way you will be sure that everything you implement can run properly, is sound, and is of a sufficient high definition. You know, there is this ambiguity between specification and code. And people tend to make a difference between specification being the what and code being something low-level programs. And maybe also this is wrong. Maybe we should consider that specification and code can be the same thing. And when you think of it, when you start building abstractions from the other side of the bank of the river, what you build is code. And if you stack abstractions, one on top of the other, it's not easy to conceive the abstractions because, as I said, it's a methodology, it's opinionated, it needs to obey a number of properties, but we are all used to abstraction. That's what we do in life. So when you stack abstractions on top of abstraction, we are doing a discrete work, and at some moment, if you succeed at imagining the right abstractions, unavoidably you reach the other bank of the river. You reach something which is not going to be UML, which is not going to be no code, but which will be concise, which will be precise, which will be compiled easily by a C++ compiler, and which will be at the level of specification. So that's what we propose to do. Let's try to propose abstractions that are at specification level that are at the same time concise and precise. And of course, as I said, that enterprise application revolve around data types and relationships, let's start with data modeling. I said that I'm not using data model on a daily basis. I never use it. Data model is tired. The word ontology could come to the rescue. So we are using the word ontology not because we want to be fancy, not because we want to show off. The word ontology has its own definition on Wikipedia. It's been used for decades in artificial intelligence, and it is gaining momentum in data science. Without reading through this definition of ontology on Wikipedia, you can go have a look if you haven't so far. An ontology is what? It's the set of types and relationships between them for a specific domain. And the definitions say a domain of discourse, because all this is coming from philosophy. This is good. This is good because somehow it says that a domain could be acquired as knowledge, that's what artificial intelligence people say, through an ontology. An ontology conveys the idea of subtlety, of nuance, of finesse, and it reconciles us with this good old rule from programming that you should type as much as you can. Because if you type as much as you can, if you display finesse in your classes, then you will sleep better at night. Because the compiler is going to ensure type safety, and you will have leverage all the capabilities of your programming language of choice in terms of describing types. In the case of C++, polymorphic types, generic types, types with constructors, types with destructors. It's very, very rich. It's so much richer than entities in an entity relationship diagram. Also, note the word discourse. I am a Wikipedia contributor. I didn't write this, but discourse is interesting. Why? Because it conveys with it the idea of language. And the theory of languages is older than the relational model, older than entity relationships. And it's something that talks about abstract syntax trees. It talks about production rules in grammars. So all this is very sound. It's not as if ontologies were relying on something which is flimsy, very new, very fashionable, and in 2 or 3 years we are going to discover that all this was just vapor and smoke. When you talk about abstract syntax trees, you are talking about trees. Trees are what's so-called in document databases documents. A document is a tree. It's a tree made of objects that contain other objects, and each of these objects can be strongly typed. You don't necessarily program this using JavaScript. So let's aim very high. Let's aim at offering a generic, by generic I mean templates, C++ toolkit allowing to describe ontologies easily to the point that the beginner could do it. So it's not meant necessarily for people who are familiar with R values and all the subtleties of C++, necessary subtleties, but is accessible to somebody who thinks right, who can analyze things in a subtle and nuanced manner. So describing ontologies easily, quickly to the point that you can write it almost while you discuss with a domain expert, with the business analyst. Let's say half a day discussion with a business analyst, half a day cleaning up your C++ code to make it so that it can compile. And maybe ask more questions, subtle questions, nuanced questions that no business analyst has ever answered, because you need to be very, very specific. And then you enter a kind of agile cycle, but the cycle is 1 day. So that's what I mean by quickly. Reusably, in the sense that when you have described all your types in an ontology, there is no keyword in C++ for ontology, but let's say it's a namespace, and this becomes reusable because you describe classes. From this, the goal is to produce automatically through a regular C++ compiler, complete enterprise applications. When I say complete, I oversell here. I'm a bit simplistic. I'm not talking about 100% of data science. This is a very complex domain. There are much smarter people than me dealing with this. I'm talking about some of the data science, some of the analytics, but all of the operational part of the application. By operational, I mean storing, retrieving, updating, these kind of things. And let's have the additional ambition that the result is faster than anything you could do by hand. How is it possible with zero-cost abstractions? I'm going to elaborate on this, but it is possible because specifically in the field of enterprise applications, there is a wall of complexity. And when you get closer to this wall, pushed by the competitive landscape, pushed by your customers asking always for more functionalities, then you start making sacrifices. I'll come back to that. It is very possible to obtain very high productivity and also gain in terms of performance. So let's start the bridge from the other side for the first time ever. So what do we mean by specification again? We mean C++ code, 100% C++ code without any pre-processing that goes directly in a C++ compiler, but which sits on very elevated abstractions. Of course, we started on our side with the standard library and Boost, which contain a number of very interesting abstractions. And on top, we added a number of arches, 5 to 8 depending on the use case. And with these carefully engineered arches, we are able to bridge hardware to specification. Remember that when you design abstractions in C++, but also in any programming language, productivity increases. It's obvious that if you use the algorithms in the standard library, you will code faster than if you were doing them by hand with pointer arithmetics. Everybody has felt that. Also, this is a compound effect. At every layer of abstraction, you gain a compound quantity of productivity. And that's not surprising. At the end, when you reach the level of specification, as I said, you can formulate the ontology almost at the same time you engage in a conversation with a business analyst. And of course, testing decreases. This is why more and more big technology companies aim at writing only specification and not legwork code, because you can save a lot on testing. And even if testing is automated, it's still very much painful. So I was saying that, and I'm sorry for the complexity of this slide. It's not as complex as it seems, and it's not as sciencey as it seems. But I was talking about the complexity wall. And you can express the complexity of an ontology by means of a formula that calculates the complexity of a graph. There is no unanimously accepted formula to calculate the complexity of a graph. There are families of solutions for this, but you can. And it's a function of the number of types and of the number of relationships. I said that this wall exists for enterprise applications. It may come as a surprise for those of you who have never developed enterprise applications, if there are some in the room, but it is the case. And it is unlike any other field in software. And when you get closer to this wall, unfortunately, the engineering cost escalates. And you are between a rock and a hard place, in the sense that your customers ask for more functionalities. The competitor has delivered something new. So you need to be denser in your ontology. I'm not going to say data model. And because of that, the engineering cost increases drastically. At the same time, performance collapses when you reach this wall. If you decide to use layered abstractions, you don't face this. On the contrary, the more you type, the safer you are. So hence these two charts, the purple one, which is a traditional approach to do enterprise application, and the green one, which is linear. Is there a point where there is a wall for the green chart? Yes, there is. Is it remotely attainable with the current enterprise applications we see in the world? I don't think so. So, let me give you a few pieces of information on what we have done. And you can do something similar, but what we have done is pretty beefy. We have around 300,000 lines of layered template abstractions. So not things that you find in Boost or anywhere on the market. These are our own. With this, you can have a general purpose C++ application server. As an example, this application server, you can use it to interact with relational databases, graph databases, you name it. You can also interact with document databases. And there are additional features in our abstractions to handle document databases because they have, as I said, a better affinity with ontologies. We have the tools to define high-definition ontologies, meaning that instead of having 4 tables to describe situation and pushing all the complexity into code that will need to be written, that will need to be tested, you can actually describe a very, very, very high-definition ontology that will have almost nothing in terms of code after. And we support automatic persistence in MongoDB. We are finishing this one. Couchbase and CouchDB, which are completely finished. Again, you don't need to use this. You can use a number of abstractions that stop at the level of an application server, able to receive JSON queries, respond in JSON, accept any kind of services. But we do automatic persistence in the case of these document databases. And this persistence, the physical aspects of this persistence are described in a configuration file. They are not described in the specification, which is very important because it makes the specification reusable. You can deploy it with Couchbase, with CouchDB, or both if you want. And this specification is also independent from the operating system, from the web server. We sit on top of either Nginx or Apache for online applications, and independent from the database. Because it was extremely rewarding, extremely satisfying, we started building a foundation ontology as well. This foundation ontology contains everything security at a higher density than anything I've seen in the past, and I've been managing teams delivering quite sophisticated security. It contains matrices to store floating point numbers, generic ones for financial calculations. It contains a cart type for e-commerce applications, and we are intending to grow this foundation ontology so that it goes even faster. Because it's one thing to go fast because you write only specification. It goes even faster if you reuse ontologies. So if you are designing an e-commerce application, better take the cart, which is already ready, nicely integrated with everything else from the foundation ontology. So I said specifications are concise and precise. Let's give you figures. 10 lines to declare a type that persists automatically. I'm not saying 10 lines which are dense with 1K per line and so on. No, very aerated lines and easy to read. 8 lines to declare a service creating a document in a database, only. 1 line, by the way, in the configuration file to describe the physical aspects of that database. 1 line to declare a multidimensional index, a KD tree, which is able to respond in microseconds, or a multidimensional request, something that no database is capable to do today on the market. It is also very efficient. I give you one example on a very conventional CPU. It's about 100 microseconds to run a service, so just the application tier, in terms of CPU time for the application tier to create a document in Couchbase, answering to a service call, which is sending some JSON information and responding with a JSON reply. Of these 100 microseconds, there are 10,000 of them per core, per second. So you see, it's quite efficient. Fighting it is a little bit difficult. It's as if you wanted to replace the standard library algorithms with your own because you think that you are going to beat it. By experience, it's hard. And it's the same thing here. So let's see a few of our high-level abstractions. And we are going to see code, I promise. I said that we support the document model. So if you are adopting the abstractions which are on top of the application server, we promote a document model. And we offer relationships, so not unique pointer, not shared pointer. We promote two families of relationships, the owns and the links, and there are several of them. What is the own? A own is a relationship between two objects that are in the same document. So the solid arrows you see on the left in the tree, which is a document, are own relationships. Of course, we have list of owns, vectors of owns, and you find the same zoology as you will find in the standard library, standard C++ library. And then we have also links. Links are totally absent in document databases, surprisingly. Links are almost only what graph databases and relational databases are actually proposing today. So the model we propose is a unification between what document databases propose and what relational and graph databases offer. Links, you can see them as dotted lines. All this looks very much like HTML, if you look at it, with URLs. And like HTML with URLs, the links can be within a document, one object pointing at another document, another object, within the same document, or between documents in the same database, between documents in two different databases, between two databases, the two documents in two database products, between two documents in two different data centers, like URLs, exactly like URLs. So obviously this integrates very nicely with document databases. Own and link are extremely easy to specify. They contain a lot. They are very layered abstractions. Typically, when you cross a link, what happens in your specification, what happens is that the system looks if the target object is in the cache or not. If the target object is not in the cache, it will load it from the appropriate document database. It will put it in the cache, and it will set the target object of the link as the one that it has just loaded. Now, if when the link is crossed, the target object is already in the cache, it will just set it. So you see, it conveys a lot of behavior. Not just this behavior, by the way, it conveys as well integrity rules. So bear with me, I'm going to show you a number of integrity rules that are either statically checked or dynamically checked, but they are all checked. An object can own another one that you would expect. An object can be owned at most by one other object. Obviously, that's the idea of ownership. Root types, so the types that are appearing at the root of a document, cannot be owned. They cannot appear in any other documents or within the same documents, for what matters. And this will be checked statically. The specification will not compile. The C++ compiler will refuse it. A document is a set of objects owned transitively by a root object. An object can own another one only if the first one is in a document. An object can possess a link to another only if the second is in a document. Seems weird. It's not weird at all when you think of it. You can point at an object with a link only if this object is in some context. If that object is not associated with some document context, then the link is forbidden. This is checked dynamically. An object can be the target of as many links as needed. Link cycles are authorized. So this is parting ways from some programming languages, from the practice of reference counting, for instance, where you are told, I beg you, do not make cycles with reference counting. Why? Because, as you probably know, it creates deadlocks. You cannot free the objects once they own each other. Here, links are perfectly authorized. And that's completely new. The system automatically maintains these rules. So these are integrity rule checks. There is also integrity rules maintenance, and it's automatic. Now, coming back to the previous slide. These rules are a little bit too stringent. Behind this, you see science. It is a little bit academic. We are relaxing them so that the specification can be written easily. So among the things that we relax, here I show you a document, and a sub-document is being cut away from this big document. So this is the purpose of this little arrow at the top, which is cut with a slanted bar. So what happens is that automatically all the links pointing from wherever to the sub-document are automatically broken. The links which are local to the sub-document are preserved. The links that start from the sub-document and point at any other part of another document are preserved as well. And this makes referential integrity a little bit more practical. This is done in cascade, meaning that the links that are broken, if they are specified as strong links, they will propagate to the origin of the relationship. So it will not stop there. If we have weak links, they will just be broken, set to 0. If they are strong links, it will be propagated. So this is much more sophisticated than relational database constraints. It is a kind of a superset of relational database constraints, except that relational database constraints fuse together two abstractions: the lifespan of information and referential integrity itself. Here, they are distinct. Finesse. We have referential integrity, which is one level, and we have as well destruction of object, which is another level. Meaning that if you have a smart pointer pointing at some objects in the sub-document, they are not invalidated. And the lifespan of object in the sub-document can be very long. They can be reused somewhere else. Now, if there is no smart pointer pointing at any object in the sub-document, they will be destroyed. And they will be destroyed immediately with the same guarantees as reference counting or shared pointers. So, let me give you some code, because you are probably dying of me talking about theoretical things. Let's see some code. I'm declaring, so the use case is an e-commerce one, and I'm describing in a very, very simplistic manner an e-commerce product. So I'm saying that there will be product characteristics, there will be something called a product category, and a product is a root. A product is a root, meaning that a product is the root, is the type which is at the root of a document. There is a small macro. We need reflexivity introspection. Nowadays, doing introspections without macros is a little bit tedious. So we are lazy, we use macros. And here what it says is that this product type has a tag, which is prod. This is your choice. This will be used for persistence. It is version number 1. Versions are floating point numbers. You can increment them, never decrement them, please. What we support is reading back an old version of a document and upgrading it automatically. Not everything falls within automatic upgrades of old documents, of course, and for that we have other tools. Then we have a reserved constructor. I'm not going to describe it. And we have our own relationship. Inside the product document, there are the characteristics. That's the way I decided to do it. And the characteristics has a tag, which is ch. That was my choice. It's going to be used for persistence. We're using JSON, Bison, XML, you name it. And we have a strong link towards the category the product belongs to. What it will do is that if the category the product belongs to is removed from the database, all the products that belong to this category will be removed automatically without any SQL running. All this is running on CouchDB, which is not the fastest of the databases, but it doesn't have SQL. Everything I'm saying works on top of CouchDB very, very nicely. Better than this, if a category is a subcategory, then in the type category that I'm not showing here, you have a strong link towards the parent category, which possibly has a strong link towards its own parent category. So you have a tree of categories, each of them being a separate document. If you remove a category somewhere in the tree of categories, all the subcategories will be removed. All the products that belong to these categories will be removed. It doesn't stop there. If you have user carts containing items that pertain to these products which have been removed, the carts will be shrunk as well and updated. And there will be no trace left of the products that were removed. So we have a lot of relationships. I said that own and link are families. So we have weak links, own list, own vector, linked list, you name it. The beautiful thing with referential integrity, which is something which is necessary in enterprise applications, usually done with a lot of code that requires lots of programmers, very repetitive work, and lots of testers doing very repetitive work, is that it has a very nice byproduct, which is object destruction. At no additional cost on top of referential integrity, you get automatic object destruction that you get in Java, that you get in all these very popular languages that are used in enterprise applications, and that make by the way, a lot of their popularity. You get automatic object destructions. Own relationships that carry a lot of behavior sit on top of smart pointers, understand shared PTR, and links contain only regular pointers. So there is a very, very frugal use of shared pointers, very frugal use of reference counting. Yet, with the rules that I have listed for you, thanks to referential integrity, links never point at destroyed objects. Never, ever. Which is very nice. I'm not going to spend time demonstrating this. You can do it ad absurdum. It's very, very amusing. You start from the assumption that you have a cycle, and then you realize very quickly that it is impossible given referential integrity rules. So automatic object destruction is so much cheaper than garbage collection. It's even cheaper than reference counting. And it doesn't suffer from the problems that reference counting is bringing, which is the cycles. You can have cycles. Enterprise applications are full of cycles. You cannot express an enterprise application ontology without having cycles everywhere. It is extremely intricated, especially using ontologies at full speed, which promote a very high definition approach of data analysis. So the higher the definition, the more intricated it becomes. And of course, cycles happen. So far better than garbage collections, the traversals, and the reason, if you are curious about it, why it is so much better, is that garbage collection is blind. It is scanning the memory, trying to find heuristics to scan it cleverly. Here we have something much more precious. We have indications on the structure of information. Strongly typed, we have categories of relationships, and we can differentiate the own and the links. So there are traversals. These traversals are needed for referential integrity. So we don't need to do extra traversals to destroy objects automatically. So it's better also than shared pointer. We don't use it much. It offers the same guarantees, and it allows for loops. All the templates you have seen, the link, the own, and so on, are templates, C++ templates, that compile with the C++ compiler in very fast, lightweight binaries. There is a video on YouTube. Look for the Metaspecs channel, and you will see an animation of this. It's almost scary, because when you propagate the removal of objects, entire documents disappear. So it is quite fascinating to see. So you should be careful when you specify strong link and weak link, because it might have unintended consequences, and this is why we are not saying that we suppress entirely testing, but the specification is doing what it is intended to do. That's what you specified. Now, replacing SQL, which is maybe the toughest of all, the most mysterious of all. So I'm not talking about replacing SQL for accessing the database. You know, SQL is used as well as a facade in terms of design patterns to access something, to remove something. I'm not talking about this. I'm talking about everything else, which is SQL, the complex stuff, the thing that keeps you awake at night, that makes SQL slow in many circumstances, the need for you to add a hint so that it uses an index and these kind of things, which is already a massive part of SQL. The reason why we can replace SQL is, first, we already have a language. SQL is another one. SQL is not object-oriented. It does a cross-cut of a part of the ontology. So every time the ontology changes a little bit, you need to go back to your SQL statement. It's so painful. And you need to test them. Not just test whether they deliver the same functionality. You need to test that they execute as fast as they did before. And this is, for true practitioners, a terrible headache. The good thing about C++ is that it is object-oriented already, so we don't need to add it. It resolves the cross-cut problem if we are able to specify what we need to do using C++ without the cross-cut of the data model. C++ is the most powerful metaprogramming model in existence. It compiles into lightweight binary code, good luck, to write by hand the equivalent. So far, of the definition of ontology in Wikipedia, we have covered, in the domain of discourse, only the syntax, which is the way information is structured. As we know in linguistics, there is something additional to syntax. It is semantics. And this is there that we are going to find the true solution to replace SQL. What is semantics? I guess that we would have as many answers to this question as there are people in the room. Let me give my definition. Semantics is something which is calculated over a document. Okay, so it does not bring anything additional to the document, but it is something which is calculated on it. This is an example of semantic attribute. So I'm taking a contract, very simplistic contract. It's the root of a document. I have an atomic piece of data, which is the start of the contract. It's a timestamp. I have the duration of the contract. And I'm saying that the end of the contract is the start plus the duration. Bit like Excel. So the end function is actually calculating, is the formula that corresponds to the semantic attribute end. If you try to assign something to the end attribute, it will not compile. End is governed by the function that you see. Of course, this is a simple example. You could encapsulate it and have the code that maintains the three pieces of data. Trust me, when you have a big document, it does not work any longer. So it works like Excel multiple ways. If you change the start, it recalculates the end automatically. If you change the duration, it recalculates the end automatically. The attribute persists in the database. You can create an index over it. So if you want to find all the contracts that have an end between this timestamp and this timestamp, you're just exploring an index in the database. So we are still using indexes in the database, but we are not using SQL for that. If in the database you had only the start and the duration, and you're performing the same task, you're going to be doing something which is known as a full table scan or a full collections scan, which is a big, big, big no-no because it is O of n complexity, so it's extremely, extremely slow. Forget about instant response time. The formula you see is a C++ function. It is compiled. It is sitting on top of the highest level abstractions. You can cross relationships in these functions. You can cross links in these functions. And every time something is changed in a document, other documents are going to get updated if there are semantic attributes that depend on this piece of data that you have just changed. So it's not equivalent at all to calculating a view, for instance, Couchbase or CouchDB, or some kind of property by running a recursive function on the document, and when you save the document, saving this piece of data. No, no. there are dependencies between documents as well. I'm told I'm soon going to run out of time. So very quickly, they are very easy to read. They are object-oriented. You can combine them. They are pre-calculated, lazily evaluated. Everything you would expect from semantic attributes. Now, a service creating a persistent document, because there are services as well. It's not just about ontologies. You don't generate an enterprise application from an ontology only. You need to specify services. Services rely on the highest level of abstractions as well. So this is a service, a basic service, which is not leveraging the built-in security. You give it the payload type that you described using the constructs that I just gave you. And you first connect to a database. Here we have a logical name, which is mapped towards a physical name in the configuration file. So we don't say here whether it is MongoDB, Couchbase, CouchDB, or whatever. It is in the configuration file. Nevertheless, this is compiled. It will look at the configuration file at the runtime. Then we build a type, and then we return. Conveniently, by the way, it will return the empty JSON object. So it's a nice accident that curly braces mean the same thing here. There is no commit. You don't need to call commit explicitly. It will be executed automatically if you don't run rollback explicitly, but you can still call commit in the middle of the service. There's no problem with this. If you retrieve a document in this service, we offer as well a very high-level function. You do get simply on the type. If you update it, let's say you change the start of the contract, the system will see that you change something in one document and will save it automatically. If some documents have not been changed during the course of the service, they will not be saved. A bit like Microsoft Office. It knows when you exit whether you change something or not. This compiles, this code, this precise code, like all the others, goes in the C++ compiler directly without any code analysis. And it compiles into a module, technically, so a binary that you can install inside Nginx or Apache. Okay? So we offer a number of things. I'm not going to list all this. We have cursors. We have everything that you would expect. I didn't have a lot of time to explain all the abstractions we had. In addition to the ones that I've shown, we have a lot of them. And they can be built as layered abstractions on top of Boost and the standard library. And I'll finish with the benefits. I have 2 minutes left. So you get backends in hours. You iterate at a rapid pace, meaning that you can produce the chunk of the enterprise application you have just been discussing with the business analyst within a few hours. And you can show it back to the business analyst to check whether it was really what he or she intended to have. You can customize implementations. Just like Bjarne is saying that we should call type everything, whether they are templates or not. Here, I didn't say that we have meta-ontologies and standard ontologies. You can have templates of ontologies. By the way, the e-commerce cart we have in the foundation ontology is a template. It's a template ontology. So you can put any type of yours inside the cart, and it will have all the behavior. As you would expect, when you combine containers from the standard library, you get very, very quickly the same things. You iterate very fast, you combine them, you have very powerful tools to describe your way of storing data. It should be the same for enterprise applications. And we think we have what makes it exactly the same. You do much more, obviously, with the engineering teams. We are not suppressing the C++ programmers. As you know, business analysts hate curly braces, hate semicolons. And the process behind producing enterprise applications requires people who think right, people who think subtle, nuanced, people who can ask questions to business analysts that nobody asked them before, that destabilize them. Is a review in the e-commerce industry on a product? Is it on a delivered product? Is it on an inventory, really? with a simple approach, it's just the table product and the table review, and you have millions of lines of code to write. It's very sad. So you can actually push the walls by having layered abstractions on top of the standard library, provided that you have the right abstractions, of course. This is the hard part. And you have better security and very, very little testing to do. And that is all. Thank you for your attention. Thank you. I'll take questions if there are.
So one of the biggest problems is data at rest and moving from one version to the next and making schema changes. How do you handle that?
Okay. It's probably the most difficult question that can be asked. So I congratulate you for pushing the right button. You know your thing, and you have probably been going through this, and it's been very painful. So what we provide by default, without any effort, is upgrade. Upgrade from the old to the new, meaning that if you remove some data, if you added some data, it will work as you expect. Now, there are cases where you need to split type in two, and this is very, very difficult. The spectrum of solutions you need to put in place in front of these kinds of problems that belong to not just one family, but many, many families, is very diverse, and I could not answer this. I'm going to answer just the most complex. So in the most complex of the situations, you will have to have the two parts of the ontology sitting side by side, you compile them, and you run an offline application that conveniently we can do with the high-level abstractions, with cursors and crossing links and these kind of things. And then you migrate with some kind of application that is yours to have the new part of the ontology populated, and then you kill the old one using the built-in, very easy facilities that we offer. It's not a very good answer that I give you, but I think there is no definite answer to this. There is no magic bullet to answer this. It's a tough question.
I don't actually have a question. I have a comment to you guys. And this is a very important talk. This is a very important new development and use of C++. Vincent and his work takes C++ into a new area of development, into a new area of problems, and attack some very, very important real-world problems using some of the traditional C++ techniques in very new ways. So please take it serious. Please notice it. Please try and understand it. For a lot of us who are not deeply embedded in the enterprise world, it's a bit mind-bending. It took me some time to absorb. Now, why should you believe Vincent? Why should you believe me that when I'm saying this? Partly because I've known Vincent for more than 20 years, and he has a very strong track record, both in business and with C++. He was the French national representative to the Standards Committee for many years. He hosted 2 standards meetings in France. He was the engineering chief for Amadeus, meaning that he has been responsible for development and deploying and maintaining one of the world's biggest real-time databases. If you've ever flown in a plane in Europe, you have used his handiwork. So please take this serious. This is a new development for C++, and it's important.
Thank you, Björn. I think we are going to stop here. I am on Discord. You can hit me on Discord. You will find me very easily on the internet. I have business cards here. If you want to pick them up, feel free. And especially if you disagree. I love disagreement. Makes me grow. Thank you.